Today we're going to be looking at section 17.7, which is on Stokes Theorem. As a guy whose name ends in an S, I want to point out it's not Stokes's theorem. When a proper name ends in an S, you just add the apostrophe to make it possessive, at least most of the time. So Field's apostrophe is how you make my name possessive. Anyway, Stokes' theorem, basically it's a generalization. It's the general case or general version of Green's theorem. Well, that's not quite fair, because remember how there were two different versions of Green's theorem? Stokes' theorem is the generalized version of the curl circulation version. Of Green's. So let's first come back to Green's theorem, the circulation/curl version of it, and remember how it looks. The circulation, a closed integral around the boundary of some surface, let's call it a curve C, is, of a vector field taken with respect to arc length along the curve. We'll usually write dr for t dot ds equals dr. Anyway, that's the shortened version of it, f dot dr, the differential arc length. Let's just take r, take its derivative, get a, actually, I can't help but wanting to explain why that's dr, so give me a second. Would you say that dr dt is the same thing as r prime? That's the Leibniz notation, that's the Newton notation for the derivative. If you just times both sides by dt, then r's derivative, in other words, the velocity vector, times dt gives you this dr. So that's shorthand for the velocity times dt. All right, fine. But what Green's theorem says is, rather than going around the boundary curve C, you can do a double integral over the region, and these two are connected by this. C is the boundary of R. But the thing that you do the double integral of is a little bit strange. It's the x partial derivative of g minus the y partial derivative of f. This is done with respect to area. And that piece in here, I've told you before, we call that the k component of curl. So what do I mean by that? Well, implicitly in here I was using f, g, and if there was a third one, h, for the components of the vector field too. Right? Let's do the curl operation to the general vector field f, and we'll see that this expression g sub x minus f sub y is what you get in the z position in the k component. I guess I don't need the title. So if f is equal to fgh, then del crossed with f, that's the curl of the vector field, is, well, you just do the usual cross product computation with partial x, partial y, and partial z in the second row. That's the components of del, and the components of f, which are f, g, and h in the third row. And when you get the I coordinate, it'll be partial with respect to y of h sub y, minus partial z of g sub z. In the j component, it'll be the z derivative of f minus the x derivative of h. And the k component, this is the one that we're referring to in Green's theorem, is g's x derivative minus f's y derivative. So one way to express this is if you take the vector k and you dot it with del cross f, you will get gx minus fy. And that's what I propose to do, to modify Green's theorem. Instead of writing it in terms of these components, g's x derivative and f's y derivative, say it in this more abstract form, the dot product of k with del cross f. That is, the double integral part of Green's theorem becomes this. Well, let's say it this way, del cross f dotted with k dA. Why is that such a big deal? I mean, it's really just notational at this point, but it makes it fall in line and become completely analogous to the thing we're going to do in Stokes' theorem. So let's see Stokes' theorem now, and then I'll sort of compare it with Green's theorem here. Now, Stokes' theorem is truly in 3D, unlike Green's, which happens in the xy plane. So you have two components here. You have a bounding curve, which you should think of as you're seeing this in perspective. This is some wiggly piece of wire. I made several attempts at showing this up in wire, but they don't actually come across that well on the video. So, but you know, something that's a space curve that comes back to the same, to an initial position. And then, along with this space curve, let's call it C, there's a surface whose boundary is that space curve. This surface could be in here, like, you know, imagine this was a weird shaped loop and you put it in a soap solution and you get a fairly level surface. It's not completely level because if the frame is warped, the surface will have to be warped to account for it, but you may have, actually, come to think of the way this is drawn, it would have some bendiness to it this way. I'm trying to get a surface in there. So, but that's just one surface that has this curve C as a boundary. Let's call it S1. There are other surfaces that might have that curve as their boundary. Imagine this was a soap film. Well, what if there was a bit of a breeze blowing? You know, suppose the wind was blowing from underneath, like this, right? Now that soap film is going to billow out and form a surface that's way out here. And I don't know if I can sketch enough of it to give you a sense of it. But let's see, that's sort of wrong the way I'm drawing it. I should go there and then come back to the other side. Okay. This is probably hopeless in terms of visualization, but anyway, it's any curvy surface that has curve C as its boundary. Here's S1 and here's S2. What Stokes' theorem says is for any surface that has C as its boundary, you can write a double integral in terms of the surface that's equal to a single integral or a path integral around the boundary. So what do? Around the boundary, you know, loop integral, you'll have something that looks like the circulation form in Green's theorem. You'll have the vector field dotted with dr. In fact,
this is exactly the left side of Green's theorem, except this curve now is three-dimensional, so there's more freedom of motion along the boundary curve. What this is equal to, by Stokes' theorem, is a double integral over the surfaces, let's just say S, of the curl of the surface. Oh, sorry, the curl of the vector field, so that's del cross F. Now, the del cross F, that's a vector, right? So to interpret del cross F, you're actually talking about a new vector field that is defined by F. But this is a whole bunch of vectors, right? What do we do when we're trying to integrate, vectors that are along some surface? Just draw a bunch of them, representative ones. It doesn't make sense to just integrate a vector because you're adding up vectors and I don't know what direction to go. What we need to do is the same thing we did with surface integrals in the previous section. Get a single number out of those vectors. And a way, and the way that actually works and makes things play out nicely, is to figure out the component of those vectors in the sort of outward direction. There's a normal vector to this surface, no matter where you are on here. And sometimes the vectors that we compute by del cross F are going to line up with those normals, and other times they're going to be, perpendicular. So a spot like here where the vector field, the curl field, and the normal vector are 90 degrees to each other, that contributes nothing to this integral. But if the things are more or less aligned, close enough to aligned, or perfectly aligned like these two guys are, then you'll get some contribution. So what we have to do then is take del cross F and dot it with a normal vector and integrate that with respect to the surface area. So I said I was going to show you how this gets reinterpreted in terms of Green theorem. And, well, part of it's really easy. This side is the same. Integral over the curve C of f dot dr. Except the curve isn't as fancy. This curve lays flat in the plane, whereas this one may have some true three-dimensionality to it. The right-hand side, that S is so big, I'm just going to, it's there, right, guys? The right-hand side becomes a double integral, and we usually call the thing that you integrate over R rather than S, because it's a region in the plane, not a surface in space. But remember how I just wrote the K component of the curl? This is del cross F dotted with K. Excuse me. And now that's with respect to surface area because this region R is flat, so we don't have the scale factor that changes area computations into surface area computations. But the fact that the ds and the dA are slightly different, that's not bad. The thing I want to point out is that the K that's here and the N that's here are really indeed the same thing. If you think about, this is happening in the 3D world versus Green's theorem happening down in the plane. The region down here has a normal vector. And which way does it point? All over that region, there's a normal vector to that region. It's a flat region in the plane. These things, they're all K's. When the surface is truly three-dimensional, then normal vectors are going to vary across the surface, unless it's a very unusual surface. Actually, no. If the normal vectors are all the same, then it's plane. Then the surface is truly a planar thing. So in general, these normal vectors point in lots of different directions, perpendicular to the surface all over the place. And we dot that with the curl. So you see the parallelism is almost perfect. And really the only difference is dA versus ds. Now what about the other version? Remember there's the circulation / curl version, which is what we've just seen. That's Green's theorem, and the Stokes theorem looks just like it. Well, the divergence form of Green's theorem doesn't have an analog for surfaces. Just, you can't make it work. And that's a little, frankly, I find that a little hard to understand why it is that we can't make a flux divergence kind of version of Green's theorem. But if we go one dimension higher, or one depth of integrals higher, you can. So you could think that the curl version of Green's theorem turns directly into Stokes's, and if you want to see the divergence version of the Green's theorem, what it's analogous to in more generality, that's the thing that's coming up, the divergence theorem. That's the last chapter in the book. Here's a funny little point that they failed to make in the textbook at this point. We can also revisit this in the next chapter, but suppose I have a little loop, piece of wire, right? I can attach two surfaces to this. I can attach as many surfaces as you like to this. Let's have an orange surface that goes up from the pipe, or the wire. And what other colors have I got? How about a blue surface that goes down below? And I mean these to be visualized as surfaces, so perhaps putting some kind of a grid on them makes it look like a surface. I don't know. Does this actually help or hurt or hinder? And it would also be connected up to the back half of the wire. I'm not sure if that's going to work for you visually, but maybe just describing it one more time. We've got this wire going around in a circuit, and then there's this surface which is connected to the wire along its boundary, and it angles down. But there's also a surface up here in the air, above, right? So that one, I don't know how well I can draw this thing. Oops, went too far. Anyway, I think you get the idea. There's a surface above and there's a surface below. Yeah, and what does that mean? Well, Stokes' theorem, if it's true, says that the integral around that simple closed curve of f dot dr is, on the one hand, equal to the double integral over this surface of del cross f dotted with the normal vector ds. So that's over let's write, just to be cute, write the s in orange here. And at the same time, it's equal to this double integral over the blue surface. Where'd my blue go? Of del cross f dot m ds. And I hope you're thinking to yourself, how could that possibly be? I mean, it's just really a strange idea that there's a vector field, the curl of the vector field we started with, curl f, that when we integrate it across the upper surface gives you the exact same result as if you integrated across this lower surface. These two things must be equal, because they're both equal to this. That's strange, and that's called surface independence. One of the places where Stokes's law, or Stokes's theorem, gets used heavily is in electromagnetism. So if you take the physics course that people always call E&M, electricity and magnetism, you find a thing called Faraday's law. Faraday's law of induction is the technical name, but I think most people just shorten it to Faraday's law. and it's got multiple versions of it. One is just that the curl of an electric field, usually the curl of an electric field is 0. But if there's a time-changing magnetic field laying around, that is, oh, this is wrong, sorry. There's a minus sign in there. Because, because of something called Lenz's law that tells you the directionality of the magnetic field's derivative goes against del cross E. So these are both vector things, right? Del cross E gets you a vector, and the time derivative of B gets you a vector. What it's saying is those two vectors point in opposite directions. That's essentially what Lenz's law is about. There's a version of this where you use Stokes's law by basically, well, you see you've got del cross a vector field here. So if you plug this into Stokes's law, the left-hand side becomes del cross E dotted with the normal vectors ds. That's going to be equal to a double integral over the thing of just the time derivative of B. Dot n ds. Sorry, I'm starting to draw on the thing. And you can use Stokes's law now to say that, or either of these, you can apply it to really either of these, the double integral of a cross product is equal to the integral around the boundary of, well, E dot dr. I think I'm getting that right. So this is a variant, a version of Maxwell's equation. I actually like the differential form of it the best, but if you integrate both sides, you get something else. And then Stokes's law says that you can turn this one that's an integral about a curl into just a path integral around the boundary, which is kind of bizarre. Surface independence in this form says that it kind of doesn't matter what shape of wire loop you have, as long as it is, what matters is not sort of this how you think about surfaces going in or out around it. So you can get to choose your surfaces in convenient ways, because what really counts is the shape of the curve, the shape of the boundary thing. That's all that determines the scope of these integrals. And this is actually the fundamental principle that makes transformers work. A varying magnetic field creates a curled electric field. When a field is curled, you can pull energy out of it. When a field has no curl, then it's it's conservative. So this is where where the conservatism of an electric field goes away in the presence of a changing magnetic field. You get this often really bizarre behavior. All right. I think that will call it for today. I'm going to provide a link to a YouTube video from the 3 Blue 1 Brown channel. Also, I'll put it on YouTube, but also in the I'll link in the Blackboard stuff. So you should check it out. It's really a cool, computer graphic, really well done computer graphic display of animations of things that explain curl and divergence, and I believe Stokes' theorem is in there as well, in a frankly brilliant way. All right, so I'll see you later.